Here's something I want to review with you a little bit more, right? So in the last lecture, we talked about any single state on the, any one qubit state can be represented as this on the Bloch sphere. Again, this is a general expression for a qubit like this. Psi equals to alpha 0 plus beta 1. But because of two reasons, we simplify it into 2 degrees of freedom. One is that alpha squared plus beta squared needs to be 1, which is the normalization condition. And other is that we don't care about the global phase. So eventually we came up with this equation. And in some literature, this is written as psi equals to cosine theta divided by 2, 0 plus sine theta divided by 2 e to the power I phi 1. Okay? And the only difference between this one and this one is because of a global phase of e to the power I phi over 2, which again doesn't matter. And because of these two numbers, the interesting about this theta and phi is that we can put it into a sphere, unit sphere in our 3D space. In every point on this space or on this surface is mapped to one of these sides. So then we can intuitively seeing how it rotates and how it works. So we can see the picture. Otherwise, in the 2D compressed, space, C2 space, it is not something we can feel. That's why we have this Bloch sphere. Yeah.
Is there an advantage to using diffusion to negative
Then this one. I don't know. I'm not aware of that. Yeah. The only advantage is in this class I give this, so that help you understand my question.
So
magnitude of A, alpha, you mean? Or this A? This one it will be less or equal to 1. Never greater. Right. So we talk about the expectation value, right? So we first talk about that, okay, what is the expectation value, for example, on sigma z, if you have an arbitrary vector psi? And we say that it's nothing but just the projection of that vector on the z-axis. Then how about this one? This is, again, is just a general 2x2 matrix, right? Not general 2x2, but formed by the inner products of the unit of a space vector and the Pauli vector. Okay? So this one represents the a magnetic field projecting in this A direction. And we say that it turns out the expectation value is what? It's just equal to this psi vector. Now, this one, don't get confused, right? First, this psi cat is a vector, of course. But it's a vector in the C2 space that we cannot see. But when we map it to the Bloch sphere, it can map to a real vector, psi, this arrow, right? This is a vector in the 3D space. And the expectation value of this psi cat for this matrix is turned out to be just like in the Bloch sphere, we do a projection or find the inner product between A and psi. It turned out to be the case. And that is the interesting thing about this Bloch sphere that can help us to gain some insight. And from now on, I actually introduce A dash and A, right? I have two different notation. It's just because they differ by 2 times. But now I will just call it A. So all the density matrix, as I showed you last time, it can be represented as 1I plus A dot sigma divided by 2. If the magnitude of A is 1, it corresponds to a pure state on this sphere. If it is less than 1, it corresponds to a mixed state. Okay? But how is it related to this Bloch sphere? That is something confusing last week when I explained to you. Maybe I did not explain well, but I will talk about that. And any questions?
Yes, sir. What's A representing? Is that vector?
A is just a vector in the 3D space, like here. So A equals to AX, AY, AC, with AX squared plus AY squared plus AC squared, square root, small or less to 1.
And how is that related to psi? Because psi is the vector state. So it's
Okay, how is it related to size? Because A dot sigma corresponds to the operator of a magnetic field, if we talk about spin, in the A direction. For example, if the magnetic field is in the Z direction, right, this A is just equal to 0, 0, 1. And so A dot sigma is just sigma Z, right? And then the expectation value of this state is equal to this one, right? So here is just say that the expectation value of this operator turn out to be just equal to the inner product of this vector and A. Right here, you don't see any magnetic field, right? So there is the correlation, the relationship between the qubit state, the space, and the Bloch sphere space.
For an arbitrary magnetic field.
For arbitrary direction for the magnetic field. That's a good question, but this is something very confusing. That's why I want you to spend so much time on this, right? You need to keep thinking about this. Yeah.
But practically speaking, in quantum computers, you're always going to have magnetic field. You either choose, typically it's CPU, X or Y.
Depends on, yeah, I don't know, I cannot say that. It depends. You don't just have a constant magnetic field. Because when you do rotation, you actually have an oscillating magnetic field in other direction, which we will cover later. But yeah, anyway, just treat this as a general treatment, because this is useful for our understanding of the density matrix. Okay. And we talk about the rotation also, right? Rotation of the complex vector or of a qubit in its hyperspace is something, again, we cannot see. But because we map the vector in the C2 space to the surface of this sphere, when it is rotating in its complex, the hyperspace, we can see it moving on this 3D sphere. Make sense? For example, when it is 0 in the complex space, in the C2 space, you have a point here. And we rotate it so it becomes 1, you will see the point here. When it is rotating, you will see that it's moving across the Bloch sphere from through some path and come to 1. Okay? And in order to visualize this, we say that this vector, this matrix, right, it can be any gate. For example, this can be equals to 1 over square root 2, 1, 1, 1, negative 1, which is a Hadamard gate. And you will say that this one, if you map to the theta and phi here and lambda here, in order to achieve this Hadamard gate, which is just rotation inside the C2 space from 0 to, for any vector, right? It is equivalent to, first you're rotating in real space by lambda, and then about the y-axis by theta, and then about the z-axis by phi. This is not how we really rotate the vector in the real space. It's just that you are rotating that vector in the hyperspace will be projected to this surface as this type of rotation. It's equivalent to this type of rotation. Okay? It doesn't, yeah. So